And let's get ready to rock and roll. So our final learning target is for this unit is on solving absolute value inequalities. And so an inequality is just like an equation, but it uses an inequality symbol. Those little like alligator mouths, a greater than or a less than symbol. And typically with absolute value inequalities, we'll be solving something called compound inequalities. And the word compound just means more than one, like together, multiple things. And so a compound inequality, you're going to have two of these inequalities on the same graph. And by graph, I really just mean a number line. It's not going to be like a full coordinate plane. And so this compound inequality means we're going to graph both of them on the same number line. For example, if I wanted to graph x is greater than -2 and x is less than 3, I want to graph both of these on the same number line. And basically, I'm going to be shading in part of the number line with my pen. And the part that I shade in has to be all the values of x, basically like the solution area, that makes not just one inequality true, but both of them. So normally, when we solve an equation, we're trying to figure out what's the one number that I can plug in for x to make it true. With an inequality, however, there's an entire range of numbers. So if I'm asking, hey, x is any number greater than -2, well, that's not just one answer. That's not just one number. There's a whole bunch of numbers. In fact, there's an infinite number of values because I could have -1 or -1.1 or -1.111, right? The list goes on. I can't list every one of them. So instead, what I do is draw a shaded area kind of on this number line. So that -2, though, that's like my starting point. So I'm going to circle that number and say, all right, so x has to be greater than -2. So where are the numbers bigger than -2? Well, they would be to the right. So I'd kind of just draw like an arrow going to the right. But that's not the only condition, because I also need to show you all the values that are also less than 3, because that's this inequality on the right. So I go to 3 on the number line and circle it, saying, hey, that's like my endpoint. But I need to show you where all the numbers that are less than 3 are located. Well, that would be to the left, that way. And since both these arrows are pointing towards each other, instead of actually drawing arrows, we're just going to shade in this entire bridge, all right, between those two dots. And what this is showing me is that the solution to this inequality are all the numbers in between -2 and +3. If you picked any number on that shaded line, that would make both inequalities true. For example, if I took the number, 2, right there, is 2 greater than -2? Yep, it sure is. And is 2 less than 3? Yes, it is. So that one number works for both inequalities because both of them need to be true. And so any number, and remember, there's like an infinite number of values here because we can look at decimals as well or fractions and things like that. So instead of listing all those out, we simply are just showing it on the graph. Say, hey, anything in this range is going to work for us. Now, this you may already be familiar with. You don't necessarily have to write this down if you remember this from earlier years in math, but you are going to need to know this. So to graph an inequality on a number line, it depends on which symbol it is, right? That inequality sign. And these rules are specifically for when the variable, typically x, is on the left side, okay? So that's if it's, x is less than this or x is greater than this. Make sure that the variable's on the left side. Then these rules always hold true. Now the first two inequality symbols, all right, the less than and the greater than symbol, these ones, they don't have this little like equal or equal to sign underneath them. And so because of that, it's an open circle, meaning you just circle the number and you leave it open, you don't fill it in. But when it's or equals to, like these bottom two symbols, the less than or equal to or greater than or equal to, whenever you circle that number, you then close it or fill it in. So that's what closed means. It means to fill in the circle. And that's telling me that my solution actually includes that number, meaning that that number is part of the inequality. It makes that inequality true. And so you close it in. And that's when it's equal, when it could be equal to that number also. Now, the nice thing about having the variable on the left side is that this like arrow pointing to the left, that's actually kind of what the inequality symbol looks like. This is a less than symbol. If you see over here on the left, that's the less than symbol. If the variable's on the left, then the inequality actually points to the direction that you would kind of shade that number line. But that's only true when the variable's on the left side. But it's kind of nice to think of this like an arrow, right? It's like an arrow pointing to the left, but only when the variable is on the left side. Is that going to work for you? The greater thans point to the right. It makes sense because if you think about it, less than means lower to the left. Like on the number line, all the smaller numbers are to the left, where the greater than means all the bigger numbers, which are to the right. So they point to the right on that number line. Who remembers seeing all this stuff at some time in the past? Okay, that's excellent. Good, good, good. Any clarifications on what I mean by any of these before we go on and look at some more? Okay. All right, so when I mentioned earlier about the variable being on the left, it doesn't have to be on the left for an inequality. But let me show you. It's a way that students often get confused by like which side the inequality is on. Where if you look at these, the top one says x is less than 3. The bottom one says 3 is greater than x. So what's different about these two? Parker's shaking his head no. What do you think? Is there a difference between these? They look different, but if we graph them, this top one says x is less than 3. So x is our variable. That's what we're trying to show. Where are the numbers that I can plug in for x to make this true? So here's 3. It's an open circle because it's not equal to 3. It's just less than 3. And x is all the numbers less than the 3. So that's all the numbers to the left. And I could pick any number to the left of that 3, and it will make that inequality true. On the bottom here, I'm saying 3 is greater than x. 3 is bigger than all the x values. And so I'm going to circle that 3 again, but which way do I shade? So don't be thrown off by the fact that this inequality symbol looks like an arrow pointing to the right. That does not mean you point to the right and shade to the right. It's actually going to be the opposite. Because if 3 is bigger than x, that means 3 has to be the biggest number. And x has to be everything smaller than it. X can't be bigger than the 3. The 3 has to be the biggest. So x has to be all the numbers to the left. So both of these inequalities are actually representing the exact same quantity, even though they look completely different. And so just like on that previous slide, how I said the arrow pointing in the right direction rule only works when the variable's on the left, what I'd suggest doing so that you don't get confused is anytime you see an inequality like this one on the bottom, where the variable's on the right, go ahead and flip it around, but please be careful. When you flip both sides of the inequality, what else do you need to change? The sign, right? That inequality sign needs to flip as well. So if I put the x on the left and the 3 on the right, just remember, this symbol here, it's eating the 3. The 3 is bigger, so make sure you make that new inequality sign the same direction. So it's still eating the 3, that bigger number. And now if you look at these, you'll see, oh yeah, those are definitely the exact same inequalities. So I just want to draw your attention to that so that you don't accidentally shade it in the wrong direction. Now I started by talking about these compound inequalities, and here's an example of one of them. Looks kind of weird, doesn't it, with like 2 inequality symbols inside of one expression? And so this actually says -6 is less than 2x, which is less than or equal to 10. So I've got a lot of information there in one single expression in this compound inequality. And it's compound because there are multiple inequalities, right? Compound just means there's like more than one. And so whenever you solve this, normally when you have a single inequality symbol and you're solving for x, like whichever operation you do to one side, you do to the opposite side. Here, though, you can think of these inequality signs as splitting our expression up. And instead of just a left side and a right side, there's a left side, a middle, and a right side. So there are 3 sides to this compound inequality. When we solve it, we still want to get x by itself in order to, represent this on a graph, represent all those solutions. And so if I want to get the x by itself, well, right now that x is being multiplied by 2. So to cancel that out, I would divide by 2, right? I want to get the x by itself, you do the opposite operation. And 2 divided by 2, that equals 1. So that kind of goes away. It's just an x. But since I divided one of these 3 sides by 2, I have to divide every side by 2. So I'm dividing the left by 2, and I'm dividing the right by 2. Go ahead and perform those calculations. And we've got -6 divided by 2 is -3. That inequality symbol, that less than symbol, would stay the same. I now have just an x by itself in the middle. And then we have a less than or equals to, well, 10 divided by 2 is 5. So this is our new inequality. -3 is less than x, which is less than or equal to 5. Now to graph this inequality, just like we did on that first example when I had 2 inequalities written, you can think of this 3-part inequality as 2 smaller ones. So I'm going to separate it out to help you kind of see this. So first, look at the inequality on the left. It says -3 is less than 5. I'm sorry, -3 is less than x. -3 is less than x. That's the first inequality that I'm looking at. Now remember, typically to graph these, we always want x on the left side. It just makes it a little bit easier to see in my head. So I'm going to flip this around. I'm going to put the x on the left, the -3 on the right, but make sure you flip that inequality sign as well. Right now that inequality is eating the x. It's the alligator, right? It's eating the bigger value. So x is actually greater than a -3. So I'm going to plot that on my number line. It's an open circle because it's not equal to -3. It's just greater than -3. And if x represents all the numbers bigger than negative 3. That means I have to show my arrow or my shading pointing to the right. I'm not going to go all the way because I need to figure out what about this second part of this inequality. What's that going to be? What's that? Yeah, that's nice and easy, right? So if I box up this right half, now you keep the x. It's like the x is shared with both inequality signs. So I'm also going to say x is less than or equal to 5. So this needs to be graphed as well. And I don't need to switch anything because the variable's already on the left side. So I put a circle on 5. And do I leave it open or do I fill it in? We fill it in because this one's or equals to. Because it could equal 5, I have to shade it in or close the circle to indicate this is part of my solution. And it says x is less than the 5, less than's to the left. So I would draw my arrow going to the left. And since both of these are kind of pointing towards each other, or both of these shadings are pointing at each other, you're going to make that bridge across between them. So you're going to shade all the way from the negative 3 to that positive 5. And that shaded bridge connecting those two endpoints represents all the solutions back to our original inequality. So back up at the top. Whoa. Okay. Don't worry, I know what I'm doing. Ish. This original inequality here, I can plug in any number between a negative 3 and a positive 5 right there for that x. And no matter what I plug in, the inequality will be true. So if I took, I don't know, let's take 0. That's an easy one to work with. If I plug in a 0 for x, well, 2 times 0 is still just 0. And sure enough, negative 6 is less than 0. That's true, right? All negative numbers are less than 0. And 0 is less than or equal to 10. That's also true. 0 is less than all positive numbers. So that worked. And any other number in between there would also make the inequality true. Questions so far on graphing these compound inequalities? Hopefully it's not too tricky. Okay. We're doing all right. So I'd like all of you to try this example here. So write down this new compound inequality. I want you to solve it for x, and then I want you to graph it. So this is going to be just like that one we just went over. So just sketch a quick number line, circle those endpoints, and then complete your shading. All right. Anyone get a sketch yet? Okay. Nice. Cool. All right. Good. And by the way, whenever you're drawing number lines to graph these, don't worry about putting in like every tick mark and every number from like -10 to 10 or whatever. The best you're gonna do whenever you get your two endpoint numbers, you can go ahead and just write those two numbers down, whatever they are. So if it's like 1 and 3, just put 1 and 3. You don't need to worry about putting everything in between. We all understand what you're showing or what you're representing. Okay. So solving this, I've got a 3x plus 6. So remember, I'm looking at this middle piece right here. That's where the variable is, and I want to get the x by itself. So I've got to cancel out the 3 and the 6. But whenever we're solving an equation or an inequality like this, we always use SADMAP, right? Instead of PEMDAS, use the opposite. So get rid of whatever's being added or subtracted first. So we subtract 6, but you make sure that you subtract it from all three sides. That gives us 3 is less than 3x, which is less than or equal to 9. And then our last step is to simply divide by 3, but we have to divide all three sides by 3. The 3's in the middle cancel, and we see 1 is less than x, which is less than or equal to 3. And so this is our final compound inequality. And to graph this, we just have our number line. And I don't need to put a whole bunch of numbers on there. Just putting those two, a 1 and a 3, is perfectly acceptable. Just make sure the numbers are in order, like the smaller numbers on the left and the bigger numbers on the right. Don't mix those up. And now to graph it, I'm going to circle these. Do they both stay open or do I fill them in? Okay, we close just the 3 because that's a less than or equal to. And then 1 is less than x, and x is less than or equal to 3. And so basically it's going to be this bridge in between those two numbers. So I just connect the two endpoints, and that's our graph. So any number on that shaded line will be our solution back to that original problem up here in the top. Any other questions on this? Okay. This one's a little bit different. I've got two different inequalities, and I want you to graph them both on the same number line, just like we did. Go ahead and give it a shot. Just solve each of these. Shouldn't be too difficult. And something's going to be a little bit different with them. All right, so solving these shouldn't have been too difficult. On the left, we just add 3 to both sides. So x is greater than 4. Over here, I subtract 2, and we see x is less than a negative 1. Now, why do I have the word or here instead? Why can't it be both of these inequalities like the last ones were? That's right. If x is supposed to represent all the values of a number that make both of the inequalities true, is there a number that's bigger than 4 and that's also less than negative 1? Does that exist? No, it can't be. It's one or the other. And hopefully you could see that whenever you would graph this inequality. If you plot the numbers negative 1 and 4, so I'll put negative 1 on the left, I'll put 4 on the right. So when graphing these values, let's see, they're both going to be open circles. But if x needs to be less than negative 1, that's going to be everything to the left here. And then x can also be greater than 4. So from the point on the right, I'm drawing an arrow to the right. So notice these arrows point in opposite directions, meaning that my solution is one of these two scenarios, but not both of them. Whereas all those previous compound inequalities, it was this kind of bridge between your two endpoints. Here, though, they're going in opposite directions. It's either less than a negative 1 or bigger than a 4, but you can't have a number that's both of those. It can't meet both of those conditions. So this is the second type of compound inequality that you'll see. There's only 2, so this is the only other one. And whenever you see the word or, like graph this or that, it means it can't be two things. Or same thing if you're solving a compound inequality problem, you get the situation where you have two values for x that are opposites, you would say it's either this or it's that, but you can't say it's both of them. We okay to move on? So let's take a look at these a little bit closer, because we still haven't done anything with absolute value yet, right? I've just kind of been building up, refreshing your mind on just graphing inequalities on a number line. But we're getting towards these absolute value inequalities. And every one of them is going to look like one of these two scenarios. Either the top one, where you've got these arrows pointing in opposite directions, or we're going to have the bottom one, where the arrows are pointing towards each other, and we just kind of make this bridge. We make this connector. So one of these two different graphs. So go ahead and just jot these down, and I want to give you some little notes on each of them. And the numbers don't matter. I just picked two random values on but those can be anything. And they could be open or they could be closed. No big difference. So this top one, I have two inequalities, but I need to show them together. Say, hey, it's kind of both of these, but not at the same time. It's either this or that. The way that you would write this out, you have two different ways. One of them could be just like that previous example where you actually use the word or. It's either this or it's that. X can be less than a negative 1, or x can be greater than 2, right? That's each of those arrows separately. X is this or it is that. So using the word or is a perfectly acceptable way to write that. And if you see the word or in one of these compound inequalities, then right away you can tell, oh, it's going to be those arrows in opposite directions. It's not going to be something that's together because it's two opposite possibilities. So that's one way you can write this. Another way that you're probably going to see is written very similarly. X is less than -1. But now, this is where it's going to get a little different. There's a symbol, looks like a giant capital U. And that symbol is called the union, which just means the combination of everything that meets this first thing, along with everything that meets this other thing. This is the union symbol. We'll see this a little bit throughout the year. It comes up much more often next year in pre-calculus, but I just want you to be aware of it. I'm not going to assess you on this or test you. I just want you to be aware of it. And a union is used whenever you have two different groups of numbers that are kind of disconnected from each other, but you want to let everyone know that your solution or the numbers you're talking about could fit either one of these conditions. So it's like my solution is all the numbers that are less than -1, and you have that entire list, combined with or unioned with all the numbers that are also greater than 2. So it's like if I listed every number less than -1 and I listed every number greater than 2, that combination of those two would represent our entire solution. So it's the union or the combination of these two. And we just use a big capital U to show that. On the bottom, we also have two ways that we can represent this inequality whenever there's that bridge connecting the two endpoints. Instead of using the word or, we can use the word and, right? It's all the values of x that are bigger than -1 and less than 2. So I could say x must be greater than -1 and x has to be less than 2. So our word choice, and versus or, differentiates between these two possibilities. Because now I can have a value for x that is bigger than -1 and smaller than 2. It can meet both of those. So I use the word and. It's this and that. The other way to represent this, and you can only do this when it's the bridge kind of connecting the two, when it's everything, when x is in between our two endpoints, that's when we can write one of those compound inequalities that we saw at the beginning of the lesson with the two inequality symbols. You start by writing the smallest value, which is -1, and then you're always going to have either a less than or a less than or equal to sign. You're always going to go from the smallest to the biggest. So you can say -1 is less than x, because x is kind of like this middle chunk, right? It's everything in between here. And then x is also less than 2. So this like three-sided inequality, compound inequality, can only be written in the second case, when x is all the values in the middle, in between those two endpoints. And I am totally okay with you using either one of those options when you write out your solutions. Or if you're solving one of these and you get those two different cases, maybe that can help you think, oh, the graph should look like opposite arrows, or the graph should look like that bridge connected together. All right, we doing okay? Nothing too crazy so far. All right, now let's start talking about the actual absolute value inequalities. So an absolute value inequality is an inequality, meaning there's an inequality symbol, and we have an absolute value somewhere around the variable. And so before we try to solve this, let's just think about some numbers that would make this inequality true. Now, this doesn't say x is less than 3. It says the absolute value of x is less than 3. So can any of you give me a number that we could plug in for x to make this true? You can just shout them out. 1, 2, what else? Yeah, negatives, right? -2. -1. Sure. How about 0? Would that work? Yeah. Can I use decimals as well? Yeah, we could do like -1.1 or +1.1, right? There's a whole bunch of them that could work. There's an infinite number. But the key thing here, which you all caught on, which I was proud to hear, is that we can have positive numbers. And we can also have some negative numbers, right? Because that inequality symbol. Now, could I use the number -5? Because isn't -5 less than 3? Good. Exactly, Aliana. She said, no, you can't use -5 because of this absolute value symbol, right? We're not saying just -5 is less than 3. We're saying the absolute value of -5, which says that's just a 5 by itself. And is 5 less than 3? Definitely not. That is not the case. So there is a limitation to these. And so if we were to graph this on a number line, it's actually going to be all the numbers that are, well, we know less than 3. What do you think the number on the left should be? What's that other endpoint? So just like this one, it's just going to be the negative version of that number, -3. Because think, if I go just in front of that, -3, like -2.99, if I take the absolute value of that, I'd get +2.99, which is less than 3. So whatever this number is, you take the positive and the negative version of that, and those are our two like endpoints. Now, where do I shade? Am I going to do those opposite arrows or the bridge connecting the two? It's the bridge, right? All the numbers in between these. And so I'm going to circle the -3, circle the +3, and then we connect this bridge. So any number between -3 and +3, even those fractions and decimals, any one of those would make this original inequality true. And so we graph that on the number line from -3 to +3, 2 open circles, and you just kind of bridge the gap in between them. So this is obviously the more simplistic version of the absolute value inequality, and we'll just do a little bit more with a few more steps. But this is the main idea of it, graphing these absolute value inequalities. So here's the big difference between solving an absolute value inequality versus an equation, because we already saw the absolute value equations last week. Now, remember those 4 steps I gave you last week also? Like isolate the absolute value, and then you draw your 2 equations, and you make one of them positive and one of them negative. With an inequality, it's the same thing, but there's one big difference. For that second equation, whenever, and that's written down here in green, but you know how you always flip that positive or negative sign for that second equation with the absolute value? The only difference with the absolute value inequality is we're going to flip the plus minus sign just like we did before, but we also need to, and look right here at the bottom, this is the most important part, you also need to flip that inequality sign. And so it is super similar to the equation, the way you solve it. Same thing, but when I write my 2 different equations, or 2 inequalities in this case, I'm going to flip one from positive to negative, and I'm going to change the direction of that second inequality sign, the one that's with the negative, or with the positive, based on which way you flip it. So this is the main new part of this lesson that I want you to have written down. And so it's at that step 3 from the previous lesson, just like equations, but instead of just flipping the positive and negative sign, we also flip the inequality sign. So to kind of show you what this would look like, if we look at our previous example, that very simple one, with just the absolute value of x is less than 3. From here, we'd write our two different equations. One of them is going to be x is less than 3, right? You don't change anything. It stays exactly the same. But for your second inequality that you're going to create, left side stays the same, but now I'm going to flip two things. First, I flip the inequality sign. So in this case, it's now a greater than symbol. And instead of a positive 3, it's a negative 3. So you change two things for the inequalities. And then you don't need to jot this down, but just to show you, if we were to graph this, we'd get our two endpoints at negative 3 and positive 3. And x is less than 3, which is this way, but x is greater than negative 3, which is that way. And sure enough, we get that same graph that we had thought about when we tried different numbers that worked. Which that's it. That's the main part of today's lesson. Let's look at some bigger examples. Let's go ahead and try to solve this inequality on your own. Now, I've already isolated the absolute value for you, that 2x plus 4. And to just go ahead and write your two inequalities and solve each of them. But remember what you have to change. All right, let's take a look at this together. Since the absolute value is already isolated on one side, we go ahead and just write our two different inequalities in this case. The first one will be 2x plus 4 is greater than or equal to 12. We don't change anything. You just remove those absolute value bars. For the second version, the left side stays the same. You just remove those absolute value bars. But now we got to change two things. We flip the inequality sign. So this becomes a less than or equal to. Instead of a 12, it becomes a negative 12. And then we just solve each of these separately. On the left side, we can subtract 4 from 12 and get 8. Then divide both sides by 2. So x is greater than or equal to 4. Did anyone else get that for the first part? Okay, good, good. Over on the right side, same steps, but now it's from a negative 12 instead of a positive 12, so we'll get a different number here. I'm going to subtract 4 from negative 12 and get negative 16. Then we divide by 2. X is less than or equal to negative 8. And so these are our two inequalities. We do need to graph them to represent this solution that meets both these conditions. So my number line, I'm just going to write my two endpoints, the 4 and the negative 8. But which number needs to be on the left? The negative 8. Just make sure the way I've set it up, yeah, there's a 4 on the left here, but that's not the smaller number. On my number line, I need to make sure that the negative 8 is on the left because negatives are smaller than positives. So I'm going to put negative 8 on the left, positive 4 on the right. And again, that's all I really need to see from you on your number line, just those two values. If you want to put a bunch of other tick marks in between, you can, but it's unnecessary. Now, these are both or equal to, right? The less than or equal to and a greater than or equal to. So when I draw my circles, we make sure we fill them in. We should close them. And what kind of situation do we have? Is it going to be the bridge connecting the two, or are we going to have opposite arrows? I heard one person say opposite arrows. Anyone agree? Yeah? So if x is greater than 4, that means from the 4, I'm going to go off to the right. Yep. And then if x is also less than a negative 8, well, all the values that are less than negative 8 would be to the left. So this is that opposite arrow situation. So it's either this or that. It can't be both. And that's it. How do you feel? This okay? Not too mind-blowing or anything like that? I just have a few other reminders for you. And I want to kind of summarize a few things. So oftentimes, whenever you're about to graph your inequality, if you look at the symbol, you can actually already tell if it's going to be the bridge or opposite arrows. This first one, absolute value of x is less than 6. I know it's going to go from negative 6 to positive 6, and it's going to be a bridge in between the two. For that bottom one, I know it's also going to go from negative 6 to positive 6, but in this case, it's going to be opposite arrows. Does anybody see how you can easily recognize which type of a graph you're going to get? The sign. Yeah. What do you mean? Tell me more.
Like if it's if the absolute value of x is less than whatever number,
Mm-hmm.
then you know it's going to be a bridge.
Yep.
And if it's not, if the absolute value is greater than whatever your number is, it's going to be a bridge.
Those opposite arrows, you mean?
Yeah.
Perfect. You did it with your hands, yeah. So Michael said, hey, if its absolute value is less than something, we know it's going to be a bridge, just like this example. But if it's the absolute value of x is greater than something else, we're going to have the opposite arrows. So that's not something you need to memorize, but it's nice to recognize that. It might help you out to know if you're graphing it correctly. It's a nice little check you can do. So I just wanted you to be aware of that. Whenever it's a less than, it's a bridge. Greater than, you're going to have those opposite arrows. Just something else for you to look for. If you want to make a note of that. And one last thing about inequalities that you may remember from back in Algebra 1. And there's another trick that happens sometimes. When you're solving an inequality and you have to get the x by itself or whichever variable you're using, sometimes to get the x by itself, you have to either multiply by a negative number or divide both sides by a negative number. When that happens, just multiplying and dividing by a negative number, the inequality symbol is going to flip directions. So if it were a less than, it becomes a greater than. If it were a greater than, it becomes a less than. This is a very small, unique property of inequalities that oftentimes students forget. So I want to specifically draw your attention to it so you remember when solving these, because that will very much change your answers. So it's just multiplying and dividing both sides by a negative number. It flips your inequality. So just to illustrate this, I have a very basic example here. Negative 4 times the absolute value of x is less than 8. Well, in order to solve this, I need to get rid of that negative 4 out in front. What operation do I use? Do I add 4? Because that's a negative 4. Should I add 4 to both sides? No. Remember, that's a common error that I see. That negative 4 is being multiplied by the absolute value of x, so I have to do the opposite of multiplying, which is dividing. So I'm going to divide the left side by negative 4, divide the right side by negative 4. And there, the negative 4's cancel out. And I'm left with just x, or the absolute value of x. Now on the right side, 8 divided by negative 4 is negative 2, but please, please, please be careful. It is no longer a less than symbol. This changes now to a greater than symbol because we divided both sides by a negative number, by negative 4. So that inequality will change. So you have the absolute value of x is greater than negative 2. From here, we write our two regular inequalities. One looks the same. X is greater than negative 2. Hey, based on this inequality symbol, can you tell me, is this going to be a bridge or opposite arrows? Yeah, when it's a greater than, remember that's going to be the opposite arrows. So I know that x can be greater than a negative 2, or x can be less than positive 2. Wait, did I mess something up? Oh, wait, maybe it is different because of the negative sign. Absolute value of x. Oh, this is a special case. I didn't even realize that when I wrote the problem. So there's something different here. If we look at this in purple, this says the absolute value of x is greater than negative 2. Hey, what happens when you take the absolute value of any number? It becomes positive. How many positive numbers do you know are greater than negative 2? Are there many positive numbers that are bigger than negative 2? All of them, right? So this is another special case. Whenever you have the absolute value of something is greater than a negative number, it doesn't matter which number I plug in for x. I could plug in any positive number or any negative number, right? Because I'm going to take its absolute value. And it's always going to be greater than a -2. So remember how on our last lesson, sometimes we had a no solution situation, like an impossibility? In this case, it's kind of the opposite. Not only is there no solution, but there's a whole bunch of solutions. I can plug in any number for x. And so if I did graph this, it would look kind of weird because it can be any number that's greater than -2 or any number less than 2. It's any number at all. So I don't even need to plot those on my graph. It's literally the entire number line because it's one or the other. 2 does work because if I take the absolute value of 2, that says 2 is greater than -2. And it is. So even if I put a -2 and a +2 on here and circled them, every number still works. So you're right in that this absolute value sign is the or word, but if x can be greater than -2 or x can be less than 2, it's kind of like from here, I'm going to the right forever, and from here, I'm going to the left forever. It happens to cover like every single number to the right and to the left. And so if you do recognize this, which again won't happen that often, we can actually just write another fancy symbol that looks like this. This is a fancy R, and it stands for all real numbers. It basically means I can plug anything into my original inequality, and it'll work. It's every real number in the world. So this means all real numbers. Again, that's not going to happen that often. This is just a special case. So we can just use that fancy R. Just like before with no solution, you had that circle with the slash through it. And if I go up to my original problem, we can actually see that that's going to be true. Any number that I plug into this absolute value, if I plug in any positive number, any negative number, it's going to become positive. And if I multiply that by a negative number, I'm always going to get a negative number. And which negative numbers are less than 8? Well, all of them. All negative numbers are less than positive 8. So because of that, any number in the world that I plug in for x would make this inequality true.
Yeah, so you just put that symbol in.
Yeah, exactly right. You would just say, hey, all real numbers. If you recognize it. If you graphed it, that would be fine too. So all real numbers is what I would write for my final solution here. And we're going to have other problems in the future and future lessons where we're going to use these symbols as well, where it's all real numbers are the solution or there's no solution at all. These things happen from time to time. So we're going to see that. Other questions on this crazy example problem? Okay. Go ahead and try this example on your own. This is our last one for the day. This is putting everything together. Go ahead and write it down. And let's see what you can do. So just like solving an equation, remember the first thing is to get that absolute value all by itself on one side. So what do you need to cancel out on the left side first? What do you need to move in order for the absolute value to be all by itself? All right, I'm going to start going through this. A lot of you are making some progress. Some of you are getting stuck at some places, so I want to still walk you through a little bit. But I'm glad you tried this. You're thinking it through. You're getting to these issues. Now we want to get the absolute value all by itself on the left. It means I've got to get rid of that 12 that's in front of it. Now, since this is a positive 12, to cancel it out, I'm going to subtract 12. So we subtract 12 from both sides. 12s cancel. And do I still have the negative sign in front of my absolute value? That's still there, right? I only got rid of the 12, not the negative sign. So we have negative absolute value of 3x plus 2 is, hey, since I subtracted 12, do I need to flip the inequality sign? Do we flip the inequality sign for subtracting? No, just multiplying and dividing, okay? So even though I see a negative 12 over there, I do not flip this sign. I leave it a greater than or equal to because I didn't divide or multiply by a negative number. Negative 5 minus 12 is negative 17. Now, that absolute value is not quite by itself yet. There is a negative sign in front of it. I like to think of this as being a negative 1. That's like negative 1 times the absolute value. And so that's what I want to cancel out next. And the opposite of multiplying by a negative 1 is dividing by a negative 1. So I'm going to divide both sides by negative 1. And on the left, the negative 1s cancel out, and I just have the absolute value of 3x plus 2 is, what do I have to be careful of right here? The sign. I did divide by a negative number now. So that greater than or equals is going to switch to a less than or equals. And then negative 17 divided by negative 1 is a positive 17. All right, so there's that extra little step of switching that inequality sign because we divided by a negative. Now I've got my absolute value isolated on one side. I now need to write my two different problems. My first problem will look just like this. 3x plus 2 is less than or equal to 17. You don't change anything for this first inequality. You just get rid of those absolute value bars. For the second one that we're going to create, the left side stays the same, 3x plus 2. But now I have to flip two things. First off, I flip the inequality symbol. So this is now going to go back to a greater than or equals. And that positive 17 is going to change to a negative 17. So make sure you've got those two differences with your second inequality. You flip the inequality sign and you flip the sign in front of that number. Now we can go ahead and solve each of these for x. So the rule, whenever you are, when you've got like a single problem here, let me erase this for you to clean it up. So from a single absolute value inequality, when you've got that absolute value isolated, and we write our two different problems, we create two of them, right? So I'm making the two separate problems at this point without the absolute value bars. One of them looks the same, but for this second one, make sure you're changing these two things on the right side. I'm flipping the inequality symbol, and I'm flipping the positive and negative sign in front of the number, okay? No problem. Any other questions before I move on? And that is the main step of this inequality, these absolute value inequalities. It's that there's two changes. That's the new part that I'm showing you. So now from here, we're going to solve the left one for x. I'm going to subtract 2 from both sides. Oops. So 3x is less than or equal to 15. Then I divide both sides by 3. So x is less than or equal to 5. On the right side, I'm going to subtract 2 from a negative 17 and get negative 19. Then we divide by 3. We see x is greater than or equal to. Now 19 doesn't divide evenly, so you can just leave this as a fraction, as negative 19 over 3, and leave your answer just like that. Don't worry about dividing it out and getting a decimal. Don't worry about switching it to a mixed number, like negative 6 1/3. Just leave it like this. It's less work, and it's easier to use in future problems. We actually like having our fractions as improper fractions. It makes them easier to work with. So then these are our two solutions. And if you noticed, that absolute value inequality was a less than or equal to. So if I think about it, I know this is going to be a bridge. This is one of those and situations. So x is this and that. It's going to meet both those. It's going to be one of those bridges. So we draw our number line. And I've got a 5 and a negative 19 over 3. Now that obviously is going to be tricky for you to place. Where's negative 19 thirds? If you do ever get that and you need to graph it, I would suggest just grabbing a calculator and dividing it out and get an approximation. So if you take negative 19 divided by 3, you get negative 6 1/3. So I'm going to put a mark at negative 6. And I know that negative 6 1/3 would be like just to the left of that negative 6. So that's one endpoint. My other endpoint is positive 5. So I'm going to circle the 5, and it's an or equals to. So I'm going to fill that in. And then it's got to be greater than the negative 6.3, and it's got to be less than 5. So it is this bridge in between the two. Okay, that one was crazy. I threw a lot at you, but that's as worse as it's going to get. If you can solve this problem, then you're going to do just fine on the absolute value test. Okay, are there any more questions on anything I talked about today? Now's a great time to ask. Or if you have a scenario, you're like, hey, Wojciech, what about if this happens? Or what if it's set up like that? Or anything that you weren't sure why I wrote something a certain way? Now's an awesome time. Do we feel okay with this? Can I get a quick thumbs showing? Up for great, down for terrible, in the middle for eh. Okay. All right. All right, let me then show you a little bit about your homework for today, and we can get a jump start on it. So your assignment for today is very simple, where the absolute value is already going to be isolated. The absolute value is already by itself. So from this step right here, you're just going to write your two separate inequalities. And so for this, here, let me take this problem and go through it real quick on the board. Oops. So this is the problem that I just saw in my delta mat. Absolute value of x plus 8 is less than 5. So you still are going to want to have your notebook out because you're going to have to work these out. You're not going to do these in your head. But since the absolute value is already isolated, I can go ahead and write my two separate problems. First one's going to be the same. X plus 8 is less than 5. The second one, x plus 8, but then you flip two things. You flip the inequality symbol, so it becomes a greater than, and I flip the sign in front of the number. And then we solve each of these separately. So here, x is less than negative 3. On the right, x is greater than negative 13. So these are our two answers. X has to be less than negative 3, and x has to be greater than negative 13. So how do we write this? Because I have to type this into Delta Math, and I can't type it like this. So we're going to use those symbols I showed you back on one of the earlier slides, either with that union symbol or the word or that three-part like compound inequality. Now in this situation, I can kind of see based on this inequality, I know it's going to be an and, or I can do that three-part inequality because x is greater than negative 13 and x is less than negative 3. So I know that it's this bridge in between the two. And so whenever you have that and situation where it's this and that have to be true, I'm going to write this as a single compound inequality, starting with the smaller number, negative 13, less than x, which is also less than negative 3. So this right here is what I need to type into Delta Math for my answer. So from here, I would type negative 13 is less than x, which is less than negative 3. And we can just type it in just like that. Now, some shortcuts for you. Not for this problem necessarily, but you see that at the bottom you do have these inequality symbols. You can click on these, or you can type it on your keyboard. And the neat thing is to do a less than or equals to. If I were typing x is less than or equal to 5, if I type less than and then the equal key, it automatically puts that bar underneath. It automatically knows to switch to that symbol. So you don't need to worry about using your trackpad and getting to this symbol. Now, if the solution were two problems that was one of those or situations, those opposite arrows pointing in opposite directions, I've got two options, which you can see down here. I've got the actual word or, and I also have this union symbol, that capital U. You can type in either one of those, and you'll get the answer correct. So if you said like x is less than 3 or x is greater than 5, because you can't have a number that's smaller than 3 and bigger than 5. It doesn't exist. So I can type in or I can use this U, this union symbol. So it's up to you. Probably the or is easier. Less than 3. And you can just type the word or. You don't have to click on that button either to make it easy. All right. For the other problem, level 3, these ones do require you to do some algebra before you get the absolute value all by itself, some canceling. And when you do that, make sure you're very careful with multiplying or dividing by a negative sign, that it flips the inequality symbol the correct way. And last, one more thing that I want to show everybody. I've got a new assignment for you that you should see in Delta Math called Optional Review, Practice Graphing Absolute Value Functions. So this is for Learning Target 1.1, where we did have an assignment, but it wasn't like random questions. You just had those 8 that I had picked out for you specifically. This optional review, it's got all these different skills broken down for you. So remember, you've got all these transformations for graphs. You've got the translations, the reflections, the dilations, that's the stretches and the shrinks. And so I've got each of those skills broken down. So if you want to isolate and say, hey, I just need practice with the flips or things like that, you can choose just to practice these problems. This is not homework. This is just for you to help you review for the test. These two at the bottom are just bigger combinations of all those transformations, but they're going to be just the these absolute value ones, where there's maybe a dilation and a translation for you to work on. If you ever get one that's got a coefficient inside the absolute value, just ignore it. Go to the next question, because that would be a horizontal stretch or compression, and we didn't cover those. So you want the ones with just coefficients out in front. That's all I'm going to be testing you on, which will be a vertical stretch or a vertical compression. And so you've got all these ones to practice. All right. Otherwise, you got 10 minutes left. The time is yours to work on your homework or to review for your test. Remember, you can even go back to 1.2, solving absolute value equations. And even though you only had to do 8, you can still do additional problems. I definitely recommend you do this. Make sure you do practice some additional problems before the test to make sure that you understand how to perform these 3 skills. Other than that, if you have any other questions, let me know. And then Wednesday, again at 9:30, log on to my Google Meet with Wojcik Math, and we'll do a little mini review to get you ready for the test. If there's nothing else, then I will talk to you all later.